Thank you for this introduction, and thank you for inviting me to this workshop. Very nice presentation. I enjoyed all of them. So what I'm going to discuss today is our prediction of giant tunneling magnetoresistance effect in antiferromagnetic tunnel junctions. So this is purely theoretical work, and it will contain two parts. So the first part will be devoted to antiferromagnetic tunnel junctions with collinear antiferromagnets. This work was largely done by, in my group, by Tim-Fu Shao, who is currently a professor at Hefei Institute of Physical Science, in collaboration with my other group members, Gautam Gurung and Ming Li, and also in collaboration with Shuhuai Zhang at Beijing University of Chemical Technology and Changbom Om, University of Wisconsin-Madison. And the second part of my presentation will be devoted to antiferromagnetic tunnel junctions with non-collinear antiferromagnets. And this work was done by the group of Jia Zhang at Shaozhong University of Science and Technology. So let me start from motivation. We know that recently antiferromagnetic spintronics became of large interest. So the idea here is to use antiferromagnetic order parameter, which is known as the Néel vector, as a computational state variable. So instead of ferromagnetic magnetization in ferromagnetic spintronics, one can use in antiferromagnets Néel vector, and rotation of all spins in antiferromagnet would be equivalent to rotation of the Néel vector, or one can think about rotation by some angle, and in all these cases we can think about some non-volatile way to record information. So similarly, one can employ non-collinear antiferromagnets. In this case, the Néel vector is not well defined, but still, if we consider two states with opposite magnetic moments, we can think about rotation, switching of the Néel vector, or we can again think about rotation of the Néel vector under some angle. So the major advantage of antiferromagnetic spintronics against its ferromagnetic counterpart is ultra-fast dynamics, which is expected for the Néel vector. So now we go down to picoseconds from nanoseconds, and this is 3 orders of magnitude difference. So this is one of the significant motivations. So another motivation comes from the fact that antiferromagnets don't produce stray fields, which implies that if you go down to small dimensions, we should not have significant interactions between antiferromagnetic devices because of the absence of shape anisotropy. So the probably most challenging and difficult thing in antiferromagnetic spintronics, and this is what many people are working on now, is that it's much harder to control and detect the Néel vector as compared to ferromagnetic magnetization. So in my presentation today, I'm going to specifically discuss a possibility of detection of the Néel vector using antiferromagnetic tunnel junctions. And this is in some way is in analogy with magnetic tunnel junctions, which are used, heavily used in ferromagnetic type devices. So let me just very briefly introduce the essence of ferromagnetic tunnel junctions or magnetic tunnel junctions. So here we have 2 ferromagnetic electrodes, which are separated by a very thin tunneling barrier, and the resistance of this junction depends on relative orientation of magnetization. So if you switch magnetizations from parallel to anti-parallel, we expect quite sizable change in the resistance, and this is what is called tunneling magnetoresistance effect. We can explain this tunneling magnetoresistance effect using a simple 2-spin channel model. So if you consider a ferromagnet being represented by 3 electron bands, which Fermi surfaces are just spheres of different radius, then we can think about tunneling as being process where on one hand spin is conserved, on the other hand transverse momentum is conserved, And then in the case of sufficiently large tunneling barrier, we can find out that conductance or transmission in this tunnel junction is simply proportional to the product of the Fermi momenta. And in this case, obviously, majority spin electrons, where we have much larger Fermi surface, would contribute predominantly in the tunneling current. So the tunneling current will be much bigger in the parallel configuration as compared to anti-parallel configuration, because in this case, we have perfect matching of the Fermi surfaces for up and down spins. Whereas here, because of mismatch, we expect that spin, the transport will have much lower transmission. So basically, due to different type of Fermi surfaces for up and down spin electrons, we have TMR. So the question emerges whether we can realize this kind of behavior in antiferromagnetic tunnel junctions. So we can imagine having two antiferromagnetic metals with parallel or anti-parallel aligned Néel vectors. And the question occurs whether we can have such antiferromagnets in such geometry where we would have change in the resistance, substantial change in the resistance when we do this kind of switching. So that would be also tunneling magnetoresistance effect, but now in antiferromagnetic tunnel junctions. So the answer to this question is probably no in those antiferromagnets, conventional antiferromagnets, which have PT or T1/2 symmetries. So PT implies here is P is space inversion symmetry, T is time reversal symmetry. So this is a combination of these two operations. In here we have time reversal symmetry plus translation for half a unit cell. So most of the conventional antiferromagnets have either this or this symmetry. And it's easy to see that in this case, we should have Kramer spin degeneracy for all bands. So because of spin degeneracy of all bands in this kind of antiferromagnets, we expect spin-independent conduction. So specifically in tunnel junction, if, for example, we think about propagation of a particular block state, because this block state will constitute one state with spin up and another state with spin down, obviously conduction will be spin independent. On the other hand, recently it was noticed that there are a number of antiferromagnetic metals which magnetic group symmetry allow momentum-dependent spin splitting. In those antiferromagnets, both PT and T1/2 symmetries are broken. So in this case, we expect to have non-spin degenerate Fermi surface. As a result, we should expect spin-dependent conduction. And there have been a number of publications which emphasize this kind of behavior. So based on this kind of antiferromagnets, we can build antiferromagnetic tunnel junction. And in fact, this kind of antiferromagnetic tunnel junction will work in a similar way as a magnetic tunnel junction. So imagine that we have two antiferromagnets, which may be the same in terms of band structure, where the Fermi surface is non-spin degenerate. So we have different types of Fermi surfaces for up and down spin electrons. Then, if you have collinear, if you have Néel vectors parallel, then we have perfect matching of these Fermi surfaces for majority and minority spin electrons. If we expect then that spin is conserved in the tunneling process, that means that spin-orbit interaction and spin scattering is very weak on one hand, and on the other hand, we assume that transverse momentum is conserved. Then this perfect matching of the Fermi surfaces will produce sufficiently large conductance. On the other hand, if you now switch the Néel vector, we'll have a mismatch between the Fermi surfaces. Up and down Fermi surfaces will be now counterparts between which the transmission will occur. And this mismatch would lead to reflection and very low transmission. So we expect much higher transmission for parallel aligned Néel vectors as compared to anti-parallel. So in some sense, it works similar to magnetic tunnel junctions. Now, let me show how we can explicitly realize this in experiment. So let us consider this kind of antiferromagnet, ruthenium oxide, which has been recently discovered and showed relatively high nail temperature, above room temperature. In this kind of antiferromagnet, we have ferromagnetically aligned 001 planes, but antiferromagnetically aligned moments between consecutive planes. So, and very asymmetric positions of oxygen atoms compared to magnetic sublattices. So because of this, this antiferromagnet has magnetic space group such that both PT and TT1/2 symmetries are broken. So as a result, we should expect K-dependent splitting, so the splitting of the bands for a given K point. And indeed, if you do theoretical computations based on these methods which are described here, and plot the band structure of this antiferromagnet, we will see that along certain directions in the Brillouin zone, there is a huge splitting between up and down spin bands, which are indicated by red and blue curves. Along certain directions, this splitting would not occur. We still have Kramer spin degeneracy driven by these glide symmetries, which this magnetic space group has. But along certain directions away from this glide invariant planes, we have substantial splitting. So I would like to emphasize that this splitting originates from exchange interaction. It's not spin orbit driven splitting. And we expect, because of this, we expect that the splitting will be and is much stronger and much bigger than the splitting which occurs due to the spin orbit interaction. So as a result, we have very different Fermi surfaces, which are plotted here. So the shape of these Fermi surfaces is similar, but as you can see, they are related by this glide symmetry. So you need to rotate or reflect the system in order to go from one Fermi surface to another. So from the point of view of transport properties, what is important is number of conduction channels. So basically, number of conduction channels is number of Bloch states available at the Fermi energy, which can contribute to the conduction. So basically, it's you can think about this as a projection of the Fermi surface, which I've shown before, on the direction perpendicular to the transport. So this is 001 plane. So what we plot here is number of bands crossing the Fermi energy along for a particular K parallel, particular K parallel corresponding to certain value of Kx and Ky in the two-dimensional Brillouin zone. And obviously it must be integer, so it's either 0, 1, or 2, shown in blue, white, and red color. And as you can see, they are quite different if you compare up and down spin channels. So if you now pick up a particular K parallel, we will see that spin polarization of this conduction channel will be non-zero. So we can plot spin polarization in two-dimensional Brillouin zone by taking into account number of conduction channels, and this is what we will have. So the fact that we have spin polarized conduction channels implies that we should have spin-dependent transmission, and this spin-dependent transmission will be different for parallel and anti-parallel lined Néel vectors. So for example, if you have parallel state, then we have for upspin electrons same Fermi surfaces, same number of conduction channels in the left and right electrode. Then if you pick up, let's say, this particular K point, we have same number of conduction channels, 1 on the left and on the right, and transmission will be non-zero. On the other hand, if you now have anti-parallel state, we have transport between up and down spin states. And now, because of no spin channels in the right electrode, the transmission will be 0. So we should expect, therefore, that the net total transmission, which is sum of all these conduction channels over K parallel and sigma, will give us higher transmission for parallel monetization, for parallel arrangement of Néel vectors as compared to anti-parallel. Now, to make it quantitative, we consider specific geometry of such an antiferromagnetic tunnel junction. So we use titanium oxide as a spacer layer between two ruthenium oxide electrodes. So there's a nearly perfect matching between lattice constants of titanium oxide and ruthenium oxide. Moreover, they have same kind of crystal symmetry. They both have rutile structure. So this is quite feasible to make experimentally. So if you look at the position of the Fermi energy and the band structure, you see that the Fermi energy is located nicely in the band gap of titanium oxide. So we can calculate them transport properties, and this is the result of computations for the case when we have parallel aligned Néel vectors in two ruthenium oxide electrodes. So what is shown here is transmission for up and down spin channels calculated in the two-dimensional Brillouin zone. And on the bottom, for comparison, I'm showing number of conduction channels. So you see that this transmission is nicely reproduces some features of this conduction channel distribution, apart from corners of the Brillouin zone where transmission is reduced because of lower transmission for this states in the tunneling barrier. Now, if you switch states from parallel to anti-parallel, you see that the transmission will be significantly reduced. From red color shown here, we go to white color, which is non-zero, is only at the center of the Brillouin zone associated with overlapping conduction channels between up and down spins. So as a result, we find that the tunneling magnetoresistance effect is as large as 500%. And it's really huge because it's really comparable and even larger than tunneling magnetoresistance in best magnetic tunnel junctions based on magnesium oxide electrodes. So this is quite a remarkable finding in our opinion. So moreover, if you look what happens as a function of energy, so instead of Fermi energy, we calculate here transmission at different energies, we find that this contrast between up and down, between parallel and anti-parallel Néel vectors remains still sizable. So we can argue then that TMR is going to be sustained under sufficiently large applied bias voltage. So I would like to mention that there have been some previous work where people considered antiferromagnetic tunnel junctions, but they considered conventional antiferromagnetic metal electrodes. And in this case, the observed or predicted tunneling magnetoresistance effect are entirely interface controlled. In fact, I would argue that it's very difficult to assume that interface is perfect. And in typical tunnel junctions, we always have roughness. So I would expect that in realistic devices, you would never have uncompensated interface. And in that sense, this kind of TMR effects, which are predicted here, likely will not be seen, or it will be very difficult to see experimentally. So in our case, it's different. Now the TMR is driven by bulk electronic structure of antiferromagnets, and in that case, TMR is robust to interface termination. So this is interface terminations we considered in the previous calculation, where for parallel Néel vectors, we have anti-parallel aligned moments at the interface. Now let us see what happens if we assume a different termination where the moments are now parallel at the interface with the same for the same parallel alignment of the Néel vectors. So we see still much bigger transmission in the parallel state as compared to anti-parallel state. So the only difference is that there is some more significant asymmetry between conduction up and down conduction channel, and this comes from interface. But the features of the TMR remain the same, and even at the Fermi energy, it's bigger. It's about 1000% now. If you now change the interface termination to be still parallel but pointing in the opposite directions, we still have a much bigger transmission in the parallel state. The only difference is that asymmetry changes, and the behavior as a function of energy remains nearly the same. We can always claim that spin-orbit interaction should not be effective in this kind of tunnel junctions. In fact, the spin-orbit interaction gives us a relatively small contribution. So this is what is shown here is the Fermi surface, where we project each state on the z, x, and y component of the spin. So z component is parallel to the Néel vector, and you see that there is a sizable z component, whereas x and y components are very small. Only at this crossing regions, there is some small contribution. And you can also see this in the number of conduction channels. Only in the regions of these edges, we have some reduction in the spin polarization. Otherwise, the spin polarization remains very large. So we don't expect any significant contribution from spin-orbit interaction. Now, in the remaining part of my presentation, I'm going to discuss a different type of antiferromagnetic tunnel junctions, now based on non-collinear antiferromagnets. And specifically, we consider this kind of antiferromagnets, manganese tin, where we have non-collinear magnetic structure aligned in the plane, 001 plane. So the system has this antiferromagnet has a hexagonal structure with this magnetic space group. Magnetic moments are in the plane and form this kind of triangular lattices. High Néel temperature, and the magnetic space group of this antiferromagnet allows us to have also non-spin degenerate Fermi surface. So in fact, if we look at the contribution from different spins in the band structure, we see more complex behaviors compared to obviously with collinear antiferromagnet, which we considered before. Now we have contributions not only from Z components, but also from XY components. In fact, here we have only contribution from XY components, and they're changing continuously depending in which band we are. So if you now rotate the Néel vector, we have rotation of this projections, and if you go from 0 angle to 180-degree angle, where we have complete switching of all magnetic moments, we basically go from we reverse all the in-plane components of the spin. Now, what is important for transport properties? Obviously, what happens at the Fermi energy. Now, if you look at the Fermi surface, we see that there are 3 bands shown here, band 1, 2, and 3. Each of them have different types of spin texture. Again, we have a complex distribution of spin texture if you project on the plane of transport. And for example, for band 1, we see that it's much more complicated as compared to what we had previously in collinear antiferromagnet. And similar to what I've shown in terms of the band structures, we see a rotation of this spin texture if you rotate the Néel vector between easy directions corresponding to 60, 120, and 180 degrees. So if you think in terms of transport properties, for example, if you have just this kind of Néel vector, and the Néel vector is parallel, we would expect tunneling, let's say, between this state and same state in the other electrode, and the matching of the spins would have high conductance. However, if you, for example, have tunneling between 0 and 100-degree rotated Néel vectors, we go from this state to this state, and the spin orientation will be flipped, and we should have reflection and much lower transmission. So based on this consideration, we designed antiferromagnetic tunnel junction, where for simplicity we assumed a vacuum tunnel barrier. So this is geometry of the tunnel junction, and what we did here, we assumed a fixed Néel vector in the bottom electrode and rotated the Néel vector of the top electrode by angle alpha. So, and this is transmission in the 2-dimensional brilliance zone for different angles of alpha. We go from 0 to 180 degrees. So we see these features representing features of the bands which I've shown before. It has kind of six-fold rotational symmetry, representing hexagonal symmetry of the crystal lattice. But what is important is that you see that the contrast, red and contrast, goes down to blue when we rotate the top electrode. And the net conductance, total conductance, if you calculate based on this transmission coefficients, goes down quite significantly if you rotate the top electrode from 0 to 180 degrees. The corresponding tunneling magnetoresistance is, in this case, 300%. It's still quite sizable and quite remarkable that antiferromagnets can, in principle, have this kind of tunneling magnetoresistance. So in addition, I would like to mention, because all the states which are shown here are non-volatile, they have same energy. We, in principle, can have 4 non-volatile states in this kind of magnetic tunnel, antiferromagnetic tunnel junctions, which is additional significance of this kind of non-collinear tunnel junctions. So these are my conclusions. And if you would like to read more about these results, you can have a look at these publications. One paper has been already published, and another paper is submitted for publication. But instead of reiterating my conclusions, I would like maybe to mention one thing which, in my view, is important. And this is question how to realize this kind of tunnel junctions experimentally. I would like to mention 2 critical things which are really important. So the first thing, it's more important for antiferromagnetic tunnel junctions as compared to ferromagnetic tunnel junctions to have conservation of K parallel, because all the effect is coming from mismatch of the Fermi surfaces in K space. So if we have mixing of the transverse momenta, obviously this effect will be lost. So in order to have them, such big effects, we need to have fully crystalline magnetic tunnel junctions and be sure that K parallel is preserved. I'm hopeful that it's possible to realize this because, for example, ferromagnetic tunnel junctions with magnesium oxide tunnel barriers, that has been realized. And in fact, large tunneling magnetoresistance effect in this kind of junctions are based on conservation of K parallel. And second thing, which is obviously very important, is ability to polarize these antiferromagnets to have a uniform nail vector. This is even more challenging. For example, in case of ruthenium oxide-based tunnel junctions, it's difficult because ruthenium oxide is not uncompensated antiferromagnet. It's compensated antiferromagnet. It doesn't have any small magnetic moment, and you cannot rotate the nail vector by magnetic field. On the other hand, in magnesium tin antiferromagnets, by symmetry, this antiferromagnet is uncompensated. It has some small magnetic moment, and it has been shown that you can flip the nail vector by applying a magnetic field. There have been some also results showing that you can use spin orbit torques to flip the nail vector, and it would be very interesting to look at this kind of behavior, and I would encourage experimentalists to look at this kind of antiferromagnetic tunnel junctions. So thank you for your attention, and I would like to stop at this, and I would be pleased to answer questions if